Now that the sample has been prepared correctly, David Neff and the students will look at the images and elemental composition of the particles found within the samples. They will be looking for particles that contain lead, antimony, and barium. The particles should be spherical and appear bright white due to the heavy metal contents. When a particle is found with these characteristics, the particle is almost certainly gunshot residue. Let's observe as David Neff and the students look for gunshot residue in their samples.
After introducing the sample and then evacuating the column, the next thing we need to do is to heat up the electron source or the tungsten filament. And it's very similar, in fact almost identical to a dimmer switch on an old style light bulb. So you're just going to have what we'd call we'll call it a variable voltage knob here, okay, that you're going to turn to heat up the filament. We want to do that kind of slowly so we don't overheat the filament and cause stress, undue stress on the filament. And the whole deal is you have to replace them when they burn out, and it takes about an hour and a half to replace them. And we do it about every month we replace a filament. So the fewer filaments we have to replace, the happier I am. So, but before you heat the filament, actually, you're going to want to turn on the high voltage. So that's that button right there. That's French for high voltage. That's haute tension. That's high voltage in French. High tension. Okay. So now we have high voltage. We have a high potential between our electron gun and the rest of the column at about 20,000 volts right now is what we have. And that voltage is what's pulling those electrons off the filament and accelerating them down through the column. Not yet though, because our filament isn't heated up yet. When you switch to this mode here, which is TV mode, that just means you're going to be able to see what's in the chamber in real time on your screen there. Then we should be able to look around and see what's happening with the sample. So go ahead and hit TV mode. And that's even kind of in focus right off. So that's fortunate. So first thing we're going to do is we're going to have to find out which sample we're looking at. And remember, we put a tab of tape sticking out the side of the stub holder. So we're going to want to find that tab of tape. What you're seeing on the screen there, those are the actual stubs. Okay. So that looks like our tab of tape, right? I twisted that piece of tape and stuck it out the side. So we'll start with this sample, and this one is going to be, what's our sample number one?
Left back.
So this is from Justin's left hand, from the back side of his left hand, okay, as he fired the gun. So you can't see much detail right now, right? But what you're seeing is that carbon tape. So let's zoom in a little bit. And so we're going to need to zoom in because if we look at that scale bar, that's 10 microns now. Our scale bar right now is 10 microns. Okay, so we're going to look for particles that are about that size or smaller. Okay, so zoom in a couple more clicks and we'll look around here. And we're looking for little spherical particles. That looks like a sphere, doesn't it? Looks pretty bright too, and heavy elements tend to be bright. Now let's see about how big that is. It's going to be more like a couple microns, but you say that may be fine. Okay, so zoom in on that little guy there. Okay, a couple more clicks. Okay, so we'll lower the contrast, and I'd say you're not very well focused at this point, huh? So once you get it about focused, then you want to use your fine focus. Okay, and you could zoom in a little more on that as well. I think our spot size is good. Whoop. Okay, even a couple more clicks maybe with the zoom. And now at this point you can use this little image shift joystick, okay, to move that around. And I think you can do a little better with the focus there. Actually, maybe I'm lowering the spot size to try to, and the spot size is the spot of the electron beam as it hits the sample. We want to maybe improve our clarity a little bit by decreasing the spot size.
Which way do I need to go?
I don't know. Try both ways. That's getting worse, I'd say. Okay, back the other way. You see where it went through a stage there that was fairly well focused? Okay. All right. So that's a suspect, I think. That's a possible particle of gunshot residue. that is about 2 microns in size. So that's about twice the size of a bacteria. Actually, that's about the size of a large bacteria. That's all the bigger that is. So we could go ahead and see maybe if this has the proper elements in it. You can see as these individual, what we call channels, as these individual channels increase in height, what that represents is another X-ray counted in that channel. So each one of these little bars we call a channel. Okay, so there's actually 1,000 channels in that spectrum. On the x-axis here is X-ray energy, and it turns out that each individual element has a specific range of X-rays that it generates. Okay, so we want to find out, what is that element? What is that element? What is that element? Where are those X-rays coming from? Just right-click on one of those peaks there. Yeah, try to get it in the center, but okay, so that's saying arsenic. It could be lead, though. Okay, there's your possibilities. Could be lead. Is it arsenic or is it lead? If it were arsenic, we'd expect to see a peak here and a peak there and a peak over there, but we don't. We just see a peak there. So let's try the lead. Now when you hit lead, look at that. Lead peak, lead peak, lead peak. Okay, it's lead. Okay, so you're going to say label, go ahead and label the series. And it's going to give us a lead on all those peaks where lead should be. Okay, that doesn't answer what this peak is, though, so let's try that one.
Right.
Yeah, right-click on that one. Potassium. Okay, I don't believe that because potassium should have a taller peak to the left of that than the peak that you actually clicked on. So let's see what else is here. Oh, look at that. SB. What's SB? Antimony. Okay. So let's go ahead and label the antimony series. So say label the series. So now we have one element that we need to find to confirm whether this is a gunshot residue particle or not. So we talked about trying to find, maybe we didn't talk about it. We need to find lead, antimony, and barium. So we found that this particle contains lead and antimony. Now we need to see if it contains barium. So you could continue to click around on the little peaks that are left, or you could just go to the element here and type in barium and see where barium should show up. Yeah, that's right, and hit enter. Yeah. Okay. Well, there's a barium peak right there. Okay. See the blue lines indicate where there should be X-ray peaks where if barium's in the sample. And if you take your left mouse click and kind of drag that spectrum up a little bit, yep. And I think we're seeing a hint of those barium peaks right there and there. As I said, it's about the size of a big bacteria. So it's a pretty small particle. Boy, that sure does look suspicious. That looks like that's more like 5 microns or so, huh? So this is actually a pretty decent looking spectrum for a particle of gunshot residue. We have barium peak down here, a relatively low energy barium peak, and you can see most of the peaks in the spectrum are representing lead and antimony, other suspects in gunshot residue. But I think what we found today as amateur gunshot residue analysts is that the larger the particle of gunshot residue is, the more difficult it is to find the barium component of it. And that's because apparently in manufacture the barium is buried in the center of the particle, whereas the lead and antimony are layers further out from that explosive component of the particle.
Thank you for joining us as we learned about the scanning electron microscope technology that has made possible the analysis of gunshot residue. When gunshot residue is found in a crime scene or on a suspect and is confirmed to be gunshot residue by the SEM, that evidence can be used in court to create proof of an individual's guilt. The lack of gunshot residue can be used in court to prove a person's innocence as well. Thanks to SEM technology, which is becoming increasingly available and more widely used, gunshot residue can be an important piece of evidence.